Hello and welcome to the last of the lectures of this week under the course titled Approximate Reasoning Using Fuzzy Set Theory, a course offered over the NPTEL platform. Over the course of the last 2 weeks, we have seen how operations on fuzzy sets can be thought of as those being performed on the unit interval 0,1. Note that the unit interval 0,1 comes here because it forms the codomain of the corresponding membership functions. We have seen that there are different possible interpretations for these operations, and we were left wondering how to choose among them. As was already mentioned, we could either look at the theoretical structures that they lead to in terms of the richness of the theoretical structures, or look at how useful they are in the applicational context. Presently, we are taking the first approach. In due course of time, we will also look at the second approach once we introduce fuzzy inference systems. Along this approach, we have seen that it was possible to introduce a latticeal structure on the set of fuzzy sets. In fact, we have introduced a complete lattice on the set of fuzzy sets. And when we looked at the corresponding structures that are available on the set of classical sets, we saw that we could in fact go towards Boolean algebra. In this lecture, we will continue looking at lattices from an algebraic perspective. We will show that at least 2 different types of algebras are possible to be imposed on the set of fuzzy sets. And once again, we will see the important role played by the unit interval 0,1. We have seen lattices from an order theoretic perspective and also from an algebraic perspective. We have seen that lattice can be thought of as a set with 2 binary operations that are closed. That means these are operations on L cross L to L, having these 3 properties of idempotence, commutativity and associativity. And we have seen that with these 3 properties, it was possible to obtain a partial order, an order relation on the set L. And we have seen that how these 3 properties of idempotence, commutativity and associativity relate to the corresponding reflexivity, antisymmetry and transitivity of the binary order relation that we have defined on. So essentially, we have also seen that what we call as the meet and join operations from an algebraic perspective on the lattice L, they actually turn out to be the supremum, the infimum and the supremum. The meet is the infimum and the join is the supremum of a pair of elements. In that sense, we have seen that lattice can be looked at from purely order theoretic point of view or from an algebraic perspective. We've also seen a few special types of lattices. First among them, from an algebraic perspective, is that of a distributive lattice, where the join and meet, both these operations, distribute over each other. We've also seen what a complemented lattice is. To begin with, we need a bounded lattice, and given an element A, we say it has a complement in B if these 2 identities hold. That means A join B should be 1 and A meet B should be 0. If this happens for every element in the lattice L, we say it is a complemented lattice. Finally, in the last lecture, we have seen what a Boolean algebra is. It's a complemented distributive lattice. Note that complemented lattice means we already have a bounded lattice underneath. Now, if you consider a non-empty set X and the set of all subsets of X, the classical subsets of X, along with its usual intersection, union and complementation operation, with empty set and the set itself acting as its lower and upper bounds, we know that it forms an algebra. And note that this was also readily translatable, and noticeable in terms of the underlying codomain of the corresponding characteristic functions, that is on the set with just the 0 and 1 as the elements. So once again, it highlights that operations on classical sets can be thought of as performing operations on the codomain of the corresponding characteristic functions. Now, we also have seen that if you take a non-empty set X and consider the set of all fuzzy sets that you can define on them, that means functions from X to 0, 1, with the usual pointwise ordering between pairs of fuzzy sets, and considering the minimum operation for the meet and the maximum operation for the join, and the constant 0 and constant 1 functions acting as the lower and upper bounds, we have seen that this structure is actually a complete lattice. Once again, we have inherited the properties from the unit interval 0, 1 with the usual order, and the meet and join being given by the min and max operations on them, and 0 and 1 acting as the bounds. We've seen that this structure is a bounded complete lattice. In fact, it is also a distributed lattice. Now, what prevents this from becoming a Boolean algebra? We know Boolean algebra is a complemented distributive lattice. So we have a bounded distributive lattice. The only question that we need to ask ourselves is this structure also complemented? Let's look at this. Now, what is a complemented lattice? A bounded lattice in which every element A has a complement B, which means satisfies these two identities. Now, this is what we actually observe. Why do we say so? Let's look at the structure. We're asking the question, is this structure complementary? Now, for complementation, we have seen that if you take any A element of L, in which case it is 0, 1, there should exist a B, again can be an element, should be an element of 0, 1, such that A join B is 1 and A meet B should be 0. So now we are going to take, for join we are going to take max, and for meet we are going to take min. Now if A is 0 and we are looking at A join B to be 1, this means 0 or B should be equal to 1. Now we are interpreting this join as max, that means it's max of 0, B should be equal to 1. It is clear that in this case that means B has to be 1. So A is 0, then its complement B is 1. Now let's verify whether this is true also for the second identity. That means we are asking the question, is 0 meet 1 equal to 0? It's nothing but minimum of 0, 1. We know that this is 0, so this identity holds. Let's look at for elements coming from the open interval 0, 1. So that means A is neither 0 nor 1. Now what we want is once again a B such that A meet B is 0 and A join B is equal to 1. This is essentially minimum of A comma B should be equal to 0. Now we know that A is not 0, so if this has to be 0, from here we see that B has to be 0. That means for every A element of 0, 1, B is its complement has to be 0. But now let's look at this. So now this is translates as max of A comma B we know is 0. We are asking the question, is it equal to 1? Now this can be 1 only if A is 1, because this is already 0. And A comes from open 0, 1, which means A is greater than 0. So now this tells us that A has to be 1. However, we know by our assumption A comes from open 0, 1, which means this is not true. This tells us that with min and max, we are not able to obtain a complement for every A in the open 0, 1 interval. 0 and 1, yes, they are complementary. They are complements of each other. So now, where does this leave us? Well, not all is lost. Why not consider other interpretations of conjunctions and disjunction? Now, what are the interpretations that we have known so far? We know min, we have looked into it. We also know that we could consider product for the conjunction, and this particular operation, which we will soon see as the Kupeshwich conjunction. So we have seen that with min and the join interpreted as the maximum function, we have not been able to show that it is a complemented lattice, even though it is a lattice. Now let's look at the case for product. So we're asking the question, if we interpret meet as product, do we get a complement for every element of the set 0, 1? Once again, let's directly consider the case where A belongs to the open 0, 1 interval. So now we are looking for a B such that A and B should be 0. That in this case A dot B should be 0. Note that A is not 0, so A dot B is 0 implies B is 0. Okay. Once again, we are seeing that for every A in open 0, 1, the complement B has to be 0. Now the question is, fine, what could be the corresponding join operation? But perhaps this is a moot question, because what we want is that A join B should be 1, and in this case it has to be A join 0, but we know that 0 is actually the identity for the join. That means A join 0 will be A, and if it has to be equal to 1, then A has to be equal to 1, but we know that A actually comes from the open interval 0, 1, which means no matter what join operation that you are considering, we are not going to get a show that the identity A join B is 1, where B is the complement of A. This leaves us with the last of the operations. Let's look at the Kupeshwich conjunction. So it is given as A and B is maximum of 0, A plus B minus 1. So now once again, consider A coming from open 0, 1. So we ask the question, does there exist a B such that A may be 0? Why not try the option B is equal to 1 minus A? So you see here, if B is 1 minus A, then this is actually equal to maximum of 0, A plus 1 minus A minus 1 is nothing but max of cancel A, cancel minus 1, maximum of 0, 0. So for the first time we are seeing that whenever A belongs to 0, 1, B is equal to 1 minus A seems to be a plausible complement of A. Note that if A comes from open 0, 1, then B also comes from open 0, 1. Now the question is, does there exist a join operation related to the Kupeshwich conjunction such that for any A here with the corresponding B as 1 minus A, that means A some join 1 minus A should be equal to 1. This is the question we are asking. Why not try this particular function? The function is x, y is minimum of 1, x plus 1. So now we need to verify if this identity holds true. That means A minus A is equal to minimum of 1, A plus 1 minus A. We see that there is nothing but minimum of 1, 1, which is 1. So that means this identity is valid. So what we see here is, if you consider among these three pairs of operations, we see that with this pair of operations, the Kupeshwich conjunction and the corresponding operation in of 1, x plus y as the join, we see that it is complemented. Note that we have a set with the model and these two operations which are closed, and now we see that they actually give rise to complement. But the question is, do they form a lattice? For lattice, we need that these two binary operations, closed though they are, they should satisfy the conditions of idempotence, commutativity and associativity. Commutativity, easily you can see, instead of x plus y, you could write y plus x. Similarly, y plus x here, plus is commutative. Associativity also follows. You can quickly verify that. What about idempotence? Let's look at that. So we know that A join B, if it is given as this, 1 comma A plus B. We want this to be idempotent, means we want this to, if A join A should be equal to, this implies minimum of 1 comma A plus A should be equal to A. Now this is minimum of 1 comma 2A. Now the left hand side could either be 1 or 2A. If it is 1, then A is 1. If it is 2A, then 2A is A, implies A actually has to be 0. So that means the only idempotent elements are 0 and 1. It means join L is not idempotent. L is equal to 0. While it is both commutative and associative, it is not idempotent. Similarly, you can show that the Kupeshwich conjunction is also not idempotent. So we see that it is not a lattice. Though it gave rise to a complement operation, it is not a lattice. Where does this leave us? Let's look at complementation as a unary operation. What is a complement? So we start with a bounded lattice. For a complement, for any given element A, we only need another element B such that these two identities are valid. Now, that means it takes an element A and maps it to another element B. How does it do that? Let's denote the complement in terms of the symbol negation. Now, if you take an A, negation of A we say is B if and only if A join B is 1 and A meet B is 0. Now, if you were to write B as negation A, this is how the above identities will look like. A join negation A is 1, A meet negation A is 0. Let us define what is a pseudo complement of an element in a lattice. Once again, we need a bounded lattice. We say an A star is a pseudo complement of an element A in L if two things happen. One, A meet A star should be 0. Yes, the first condition. The second condition is whenever B is smaller than A star, then A meet B should also be 0. Note that what this says is the A star that we are choosing should be such that it is the largest element among all elements of L, such that A meet A star is 0. If there is a B which is smaller than A star, then A meet B also should be 0. In that sense, we are seeing that a pseudo complement is unique because it is the largest one in the lattice, the largest element such that A meet A star is 0. However, notice that there are also other elements such that A meet the meet of A with those elements also are 0. So in short, a pseudo complement of an element A is the largest element such that A meet that element is 0. Now let's compare the concepts of complement and pseudo complement. For pseudo complement, we have only the first condition, not the second one. Consider this now familiar lattice, that 0, 1, the unit interval with the usual order, and min and max are taken for the meet and join operations. And consider this function. Note that now we are looking at complement as a function. Clearly A star is a function on 0, 1. It takes the value 0 whenever A is not 0 and takes the value 1 when it is 0. Now the question is it a pseudo complement on this lattice? Fortunately, yes, it is a pseudo complement on this lattice. How do we know this? Let's look at this. So what we have given an A star is 1 if A is equal to 0, 0 if A is not equal to 0, that means A belongs to open 0 closed 1. Now what we need to show is this. A and A star is actually equal to 0. Also, if there is a B less than or equal to A star, then they should imply that A and B is 0. Now, if A is equal to 0, we see that A star is 1, which means A meet 0 meet 1 is nothing but minimum of 0, 1, it is 0. So this is valid. Now, since A star is 1, B could be anything less than 1. So let's assume that B is strictly less than 1. Now what we need to show is A and B should be equal to 0. But note that A is 0, so this is interpreted as minimum. Minimum of 0, B we know is actually 0 because B, if you take it to be between these, it is 0. So for A is equal to 0, we see that both these properties are valid. Let's take A to be from the open interval, open 0, close to 1. Then by this function, we know that A star is 0. Clearly now, A meet A star is minimum of these two, which is 0. And since A star is 0, the only B that can be smaller than that, or smaller than or equal to 0 is itself. There is no other element which is strictly less than 0. So then essentially B is 0. And we have already proven that for that A and B is 0. So we see that this operation that we have here gives you a pseudo complement on this lattice, and hence this lattice becomes a pseudo complemented distributive lattice. Let's not stop at that. We discussed and said that we should try and get as rich a structure as possible. Now once again compare complementation and pseudo complementation. We see that pseudo complementation differs in that the second identity is not valid. Stone introduced a particular identity which is given like this. You would see the close relationship or resemblance with respect to the second identity, which is A join negation is 1. However, notice that negation A, which is the complement of A, is replaced by the pseudo complement of A star, and A itself is replaced by double pseudo complementation, A double star. Now, a pseudo complement may or may not satisfy Stone's identity, but if a pseudo complementation exists on a lattice hill, and if it satisfies Stone's identity, and if that lattice happens to be a distributive lattice, note that even pseudo complementation is defined only on a bounded lattice. So if a lattice L is distributive, has a pseudo complement which also satisfies the Stone's identity, we call it as Stone algebra. And what is interesting is, what we have seen as a pseudo complemented distributive lattice, under the same pseudo complement, it can be shown that it is a Stone algebra. That means this particular function actually satisfies the Stone's identity. Once again, this is not very difficult to see. Now what we have for any A star is given like this. It is 0 if A belongs to open 0, close to 1, and 1 if A is equal to 0. And what we need to show is only this: A double star join A star is equal to 1. Now, this translates as max of A star 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 should be equal to 1. Now if A is 0, then A star is 1, A double star is 0. So when you substitute here, you see that this is 0, this is 1, max of these two is 1. If A belongs to open 0 close to 1, then A star is 0 and A double star now is actually 1. Once again, max of these two is 1. So clearly, this pseudo complement operation satisfies the stone identity. So it becomes a stone algebra. Well, let's see whether we can get yet another algebraic structure. We are all familiar with this structure, the De Morgan algebra. But before that, let's look at complementation itself. We have now two different types of complementation, complement and the pseudo complement. And we have also investigated a little bit on the stone's identity. So we have said that the stone's identity differs in the sense that instead of A, it asks for double pseudo complementation. Now, we said we could look at complementation itself as a unary function from L to L. It is clear that it inverts 0 to 1 and 1 to 0. But if you also insist on this, this would look like this. Double negation of A is A. This is normally called the involution or the involutive property. So if you have such a complement operation, then these two are essentially same. For A, instead of A double star, we could as well use A itself. Of course, here we are talking about complementation. It could also be pseudo complement. Now, since the L is fixed as 0, 1, the complementation function can be looked at as a unary function from 0, 1 to 0, 1. We have seen that this is A star is a pseudo complement. Now, this does not enjoy the property that A double star is A. Why not consider introducing another function which may enjoy this involutive property? One such function is this eta function, which is defined as 1 minus x. Eta of x is 1 minus x. Note that clearly eta of 0 is 1, eta of 1 is 0, and eta of 1 minus x is 1 minus 1 minus x, which is equal to x. So that means eta of A is actually A. So this seems to be a good candidate to be considered for complementation operation with involution. Now, what is a De Morgan algebra? Once again, it's a bounded lattice, a complemented lattice, such that these two identities hold. Now, this is perhaps very common to us from our school days. If you were to think of it in terms of sets, if A and B are sets, all we are saying is A union B complement is A complement intersection B complement, and A intersection B complement is equal to A complement union B complement. Now, once again, this is also known to us that every Boolean algebra is a De Morgan algebra. We just looked at an example from in the sense of looking at pairs of classical sets. So every Boolean algebra is a De Morgan algebra. Now, can we at least come up with a De Morgan algebra on the set of fuzzy sets? Which means we want to look at the corresponding underlying codomain of the membership function, which is once again the 0-1 interval. Let's look at the usual now familiar lattice, but instead of using the pseudo complement as we defined earlier, let's use this eta function, which is 1 minus x. Now, the question is, with respect to this eta, does it satisfy the De Morgan laws? It can be easily verified that yes, with eta, both min and max do satisfy these De Morgan laws, and hence it becomes a De Morgan algebra. So in this lecture, we have seen at least two different algebras on the set of fuzzy sets, a stone algebra and a De Morgan algebra. Once again, we have seen that min and max still enjoy their place in the setting, and many of these results were possible because we were inheriting the properties from structures that are available on 0. Where do we go from here? What about other interpretations of conjunctions? Note that the Kupeshwich pair of conjunction and disjunction, they came very close to giving us a lattice. They enjoyed complementation. They were both commutative and associative. It was only at idempotence they fell. Because they were not giving us a lattice, should we discard them? Well, definitely not. They will help us going forward. And what kind of structures do they give? So this becomes the topic for the lectures that will be delivered in the next week, wherein we will specifically look at conjunctions on the unit interval 0, 1, which also are conjunctions on the set of fuzzy sets, given a pair of fuzzy sets, the conjunctions that are possible, the different interpretations. And we will look at one particular generalization of a conjunction from the classical two-valued logic and discuss the algebraic, analytic and order theoretic aspects and come up with results which will be useful later on when we deal with applications or in the theoretical setting of applications. This book could be a good resource for you if you would like to check up more on the topics that we have touched upon in this lecture. Thank you once again for being with me through this lecture and hope to see you soon in the next lecture. Thank you.